Welcome to Fluids Day 3, Part 2. These are 3 problem examples. The first example is a Venturi tube. So water travels through a hose, a diameter of 9.6 centimeters with a velocity of 1.3 meters per second. And the hose is over on the left, 0.1. Water flows out through a nozzle of diameter 2.5 centimeters. What is the speed of the water coming out of the nozzle? I've shown you the answer is 19 meters per second if you decide to do this on your own. And then we change the problem slightly. If in the hose the pressure is 350,000 pascals or 350 kilopascals, find the pressure in the nozzle. Okay. So what I would do first here is use the continuity equation. And here is the equation of continuity. Left side would be the area of the hose and the velocity of the water in the hose. Now we're given a diameter, but I know that an area of a circular region is pi r squared. And I know r is diameter divided by 2. So when I square it, I get d squared over 4. So I've done that with both sides of the equation. I have pi on both sides, so when I divide by pi, those cancel. I have divided by 4 on both sides, so the 4's cancel. And I get velocity times diameter 1 squared, that would be the hose side, equals velocity 2 times the diameter 2 squared, that's of the nozzle. I know the velocity on the hose side is 1.3. The diameter of the hose side is 9.6. I have to square that. I'm solving for the velocity in the nozzle. The diameter of the nozzle is 2.5. I square that, and I find that the velocity is 19 meters per second on the nozzle side. The next thing I have to do is use Bernoulli's equation. And Bernoulli's equation says pressure plus the kinetic energy per volume plus the potential energy per volume is constant everywhere on the hose. So the left side is the hose, the right side is the nozzle. But what we are assuming here is there's really no change in height of the fluid. So y1 equals y2, which means these terms are equivalent and can be subtracted out on both sides of the equation. So I can solve for the pressure coming out of the nozzle. I was given P1, 350 kilopascals, so 350 kilopascals is 350,000 pascals, plus 1/2 the density of water, which is 1,000. I was given the initial velocity of the water in the hose, that's 1.3 meters per second, and I solve for the velocity of the nozzle, and I find the pressure of the water coming out of the nozzle is 170 kilopascals. Now here's an insight. The pressure in the nozzle is less than that in the hose. Where does that stored energy go from the hose? Well, it gets converted into kinetic energy as the water passes through the nozzle. Okay, example number 2, I have water flowing through a hose at a constant speed, at least in the first part of the problem, which means V1 equals V2. I've written that down over here. And it goes up a step, and the step is 20 centimeters. Now remember, you have to convert that to meters, so I've chosen my reference location at Y1 to be 0. And that means that 20 centimeters is 0.200 meters at location Y2. I have pressure 1 at 143 kilopascals, which I have to change to pascals in the equation, and I've done that here. And I want to know what the pressure is at the top. So I've written Bernoulli's equation, but as we said, we have a constant speed, so these two terms are equal, and I can subtract them on both sides. So I also have y1 equals 0. That is my reference location, h equals 0. And so I substitute in for pressure 1. I'm solving for pressure 2. Density of water is 1,000. I happen to use 9.81 here. You can certainly use 9.8. The answer will be slightly different. And height y2 is 0.200 meters, and I end up getting 141,000 on my calculator, which is 141 kilopascals. The problem, I talk about changing the cross-sectional area of the hose. So at the top, it's half of what it is at the bottom. So I just say that my cross-sectional area at the top is x, and then it would be 2x at the bottom. Now I know at the bottom of the step, which is V1, I'm given that the velocity is 1.20 meters per second. So I use my continuity equation and plug in my given information to solve for V2. Turns out, when I substitute these in, I get an x on both sides, which divides out. And I find that V2 is twice V1. So V2 ends up being 2.4 meters per second. Okay, so I usually use the continuity equation first, and what you'll find in the next slide is that you have to use Bernoulli's equation next. This is pretty typical. If the cross-sectional area of the hose at the top is half of that at the bottom, we found that the speed, and I didn't write that down here, but the speed at location 2 was 2.4 meters per second. And we had the original speed at the bottom of 1.2 meters per second. You should always write down your given information on the AP test. Okay, next thing you do, write down Bernoulli's equation without substituting in numbers, because that'll give you usually 1 point on the test. And then I substitute in my given information: the pressure, density of water, velocity of the water at the bottom of the step. I'm now solving for pressure 2 at the top of the step. Next term, 1/2 density of water times the velocity, which we solve for in the continuity equation, plus density of water times the acceleration due to gravity times the height of the step. Now again, I use 9.81. You certainly can use 9.8. And what I get for pressure 2 is 138,878 pascals, which, if I use sig figs, is 139 kilopascals. This is an interesting problem. I have a container of water at the top, which we are assuming always has a height of h. Okay, we've done a problem like this before. It comes out a small hole in the bottom. So again, we did a problem like this, problem number 1, I believe, or maybe it was on a different day. And that H is 0.5 meters below the hole in the first can. So once we find the velocity of the water coming out here, what we have is a horizontal projectile motion problem. We have the height, H, which is 0.5 meters. We can find out how long the water is in the air, and then we can find out, based on the time and this initial component of velocity, how far we need to put the second can to catch the water. Okay, I'm going to use what we learned before to find the velocity of the water coming out of the small hole at the bottom. And that's really like a conservation of energy problem. So I find the velocity ends up being the square root of 2 times the acceleration due to gravity times the height of the can, which we were told was 0.15 meters at all times. So I find the velocity of the water coming out of the top can to be 1.7155 meters per second. Now, certainly if you were to write that on the AP test, I think you should use sig figs, but I keep that to do the rest of my problem. Now, I have a horizontally launched projectile, which is the water, okay? And that would be the kinematics equation I would use. But certainly there is no initial vertical component of velocity. So delta y ends up being 1/2 at squared. Well, that's equal to 0.5. That was given in the initial problem. So that can is 0.5 meters higher than the location of the object we're catching the water in. So I can find the time that the water is in the air, that depends only the height off of the ground, to be 0.3193 seconds. Now, how far does the water go in the x direction? Well, it's simply the velocity, initial velocity in the x direction, which by the way doesn't change. And we found that up here to be 1.7155. And you simply multiply that velocity by the time we had, and we find that the water shoots out horizontally 0.5477 meters. And again, if you're doing this on the AP test, I would suggest sig figs.